In this video, we're going to continue to simplify radicals. So we need to remember a couple of rules. No radicands contain fractions. So radicands is the number inside of a radical. It cannot have fractions like this. And then no radicands appear in the denominator fraction, or no radicals appear in the denominator fraction just like these. So we're going to focus on, again, our nth roots. So here we're looking at fifth root here. Now we always take a look. Now number one, could we divide? Like if we put it all under the same radical, 7 over 8, we cannot divide it, right? So we can't simplify how we did previously. So what we want to do is something a little bit different. What we want to do is first, let's simplify or factor the denominator. So remember with the fifth root, that 5, that tells us how many of something we need before it's perfect. So let's break down or factor out the denominator. And so fifth root of 7 doesn't change, and that's okay. We can have a radical in the numerator. But the denominator, 8, I hope we see that that is 2 times 2 times 2. So now looking at this, we want to have 5 of a number. So we have 3. So how many do we need? We have 3 2's. We need 2 more 2's. So in order to add more of those 2's, to put 2 more 2's there, we're going to multiply by the fifth root of 2 times 2. Okay, so it's important that it's the fifth root. It can't be a square root because fifth root and square root, they're different, right? They're not like. So they have to be the same. So that's one little just minor thing that is important, is that when you are multiplying, you have to multiply by that same index. So fifth root of 2 times 2. So now we can multiply them together. So let's simplify. We have fifth root of 7, and then in the numerator we have 2 times 2. Now in the denominator, I have this 3 2's and then the 2 more 2's that I multiplied. So now I have 5 2's, and now that is perfect. So we have fifth root, and we know that we cannot break down 7, 2, and 2 any further, so let's just multiply the numbers together. That's 7 times 2 times 2, or 7 times 4, which is 28. Then at the bottom, we had the 5 2's, and so it comes out just as a normal 2, or constant of 2. And so now that is simplified. There are no more radicals in the denominator, and so forth. So try out these examples here. So again, the very first step you want to do is to break down the 4. You don't want to multiply 3 4's, for example. In this example here, fifth root of 8, we don't want to multiply 4 8's, right? That's a really, really, really large number. I mean, you could do that, but what you're going to find out is the numbers get really large, and then you have to simplify, which will take longer. So pause the video, try out number 1 and number 8, please. So if you tried this out, so for the first example, you would break down the 4. So 4 breaks down to 2 times 2. So that index tells us we need 4 total. And so you multiply by the fourth root of 2 times 2 to the top and the bottom. Again, that's a form of 1, right? Fourth root of 2 times 2 over fourth root of 2 times 2, that's just 1. So it doesn't change it at all. So then you simplify, so you can put all under the same radical. So 19 times 2 times 2, that ends up being 76. Then when you put the 2 2's under here, under that fourth root, then you circle all 4, and then it just comes out as a perfect 2. Number 8, so it's under one radical, so we can split it up. Fifth root is 5 over fifth root of 27. And again, break it down. So 27 breaks down to 3 times 3 times 3. So the 5 again tells us we need 2 more 3's. So therefore we multiply by the fifth root of 3 times 3 to the numerator and denominator. And then you simplify all the way. You end up with 5 times 9, which is 45. So fifth root of 45 over these 5 3's with the fifth root, it says a 3. So let's practice a couple more problems here. So if we have a square root, cube root, and fourth root, we do the same thing. So just remember with square root, so we don't have to break it down, right? It's 11. And so we're going to multiply by the root 11 over root 11. So what this becomes is 2 root 11 over Square root of 11 times 11, now remember that this is a square root, so we need 2, so it comes out as a perfect 11. Now for the cube root, so again, let's break it down. Cube root of 3 times 3. We need another 3, so cube root of 3 over cube root of 3. We will end up with 4 cube root of 3 all over 3, right? Because then there's 3 3's, cube root, and it's perfect. The last one, 3 over 4th root of 125. So 125 is 5 times 5 times 5 because it's 5 times 25. 25 breaks down to 5 and 5, so it's 3 5s. Now we're missing one more 5, so multiply by the 4th root of 5. Now notice because the number's outside, it's just going to go outside of the radical, so it doesn't go inside like in our previous examples where they were multiplied and it both went inside, right? So if they're inside, you multiply them together and you combine them. But if it's outside, it's not in a radical, then it just multiplies to the radical and stays outside like this. All right, so we're multiplying 3. So this becomes 3 4th root of 5. Now we have 4 5's in the denominator, so it's just 5. So try out these 3 examples on the right. So if you try this out, again, remembering that if you need to, break it down. So for square root, we don't need to, it's just 3, which is fine. So we multiply by root 3 over 3, and then we will end up with 5 root 3 over 3. For the second example, we have cube root of 49. And so 49 breaks down to 7 times 7. So we need one more 7. So we're going to multiply by cube root of 7 over cube root of 7. Then when you simplify, you get 8 times cube root of 7 over, we have 3 7s, so just a 7. The last one, we have 2 4th root of 27. So we need 4 of a number. 27 breaks down to 3 times 3 times 3. We need one more 3. So therefore, we're going to multiply by 4 root 3 over 4 root 3, 4th root of 3. And then you have 2 times 4th root of 3 over just 3. Now we're going to look at some denominators with the sum or difference involving square roots. So here are our examples. So notice there are square roots, but we just have a number with it. So we have to deal with these a little bit differently. So a denominator with the sum or difference involving square roots, we have to multiply both the numerator and denominator by what's called the conjugate. Conjugate of the denominator. So the conjugate, it has the same term but opposite sign. So for example, if we have an a plus square root of b, so I'll just use kind of like our examples we see here at the bottom, then the conjugate has the same terms, a root b, but the sign in the center is opposite. Okay, so if it's positive, then it's negative. Now, if we had a minus root b, for example, then what would we multiply by? A plus square root of b. Okay, so we have 7 over 5 plus root 3. Now, just to show you why you cannot multiply by just the square root. If I had 7 over 5 plus root 3. Now, what we used to do was just multiply by root 3 over root 3, right? Square root. Now, notice what happens when I do that. I get 7 square root of 3 over, and I'm going to have to distribute. This becomes 5 root 3 plus root 3 times root 3. Okay, so 7 root 3 all over 5 root 3. And then this is just root 3 squared, so that's plus 3. But notice it didn't make it any better for us. We still have this radical here, which is not what we want. So we don't want to do that. Okay, so you can start to do that and you'll realize that it doesn't work. So to get rid of it, we do the a plus b, a minus b pattern, the conjugate. And if you remember, when you multiply this out, this ends up being a squared minus root b squared. So we don't have the middle terms. We won't have a square root anymore. So that's why we do that. So let's try this out. We have 7 over 5 plus square root of 3. So we're going to multiply by the conjugate. So if we have 5 plus root 3, what is going to be the conjugate? So that will be 5 minus root 3. So now let me just do this the long way. So notice 5 times 5, if I'm multiplying the denominator, 5 times 5 is 25. So I'm doing FOIL first and then outside. This is a positive 5 minus root 3. Or sorry, it's a negative 5, right? So 5 times negative root 3 is a negative 5 root 3. The inside is a positive 5 root 3. And then last is going to be so positive and negative is negative root 3 and it's squared. Notice that the middle two terms cancel out. That's what I was talking about in the beginning right here. When you multiply by the conjugate, we won't have that middle term, right? It disappears. So notice this is just the 5 squared minus the b squared. So you don't ever have to do this long way for it. Then the top we have to distribute. So this becomes, I'll write it the long way, 7 times 5 minus 7 times root 3. Now let's simplify. 7 times 5 is 35 minus 7 root 3. And then we have, everything disappears here, we have 25 minus square root of 3 squared. It cancels out that square root, right? So we have minus 3. So then let's simplify. We have 35 minus 7 root 3 over 25 minus 3, which is 22. And now that is simplified. We no longer have a radical in the denominator. Now remember, we cannot add 35 and minus 7 root 3. They are not like terms, so do not try and simplify that any further. That's as far as it goes. So try out example 9. So first you have to determine what is the conjugate of 6 minus root 2. So what is the conjugate of 6 minus root 2? So that would be 6 plus root 2. Okay, so pause the video and finish this out. So if you tried this out, you would have gotten 18 plus 3 root 2 over 34. So another way that I wrote this is I just did the a squared minus b squared pattern. And so I wrote 6 squared minus root 2 squared. So that would cancel out the root, square root, and then 6 squared is 36. Last thing is we're going to simplify variable expressions. So we're going to assume all variables are positive. And we've actually done something similar to this before, so it's just kind of practice, more practice. We have 4th root of x to the 4th over y to the 8th. And so let's split up the nth root, so 4th root of x to the 4 over 4th root of y to the 8th. And so we could break down the denominator, for example. So 4th root of x to the 4, we know there's 4 x's, so that's okay. But we can break down the denominator as y to the 4 times y to the 4. So then we can circle out our 4's. So we're left with x over y times y, which is y squared, right? This becomes y, and this is a y. And so you multiply, so x over y squared. Letter B, we have x and then cube root of y to the 8th. So y to the 8th, we can change that. So we want it in groups of 3. So just as a reminder, we want that exponent has to be less than the nth root of 3. So we want it to be groups of 3. So 8 is going to be 3 plus 3 is 6 plus 2 more is 8. So we can break down y to the 8th in this way. Y to the 3rd times y to the 3rd and y squared. Remember, we can add those exponents together. 3 plus 3 is 6 plus 2 gives me 8. So now I notice that I cannot, or I'm missing one more y. And remember, we cannot have radicals in our denominator. So what are we going to have to multiply? We need one more cube root of 8. So let's multiply by cubed root, not cubed root of 8, cube root of y, because we need one more y to have a perfect number 3 here. So we had one more of them, or multiply one more of them. So now this becomes x cube root of y, we just multiplied across. And then we're going to have 1, 2, and 3 y's here. So 3 y's come out. So our final answer is x cube root of y over y to the third power. So now try out these next few examples. 1, 2, oh, there's 2 2's. 1, 2, 3, and 4. If you tried this out, you would have gotten, so you can break down x to the 10th as x to the 5th, x to the 5th. So there's 2 of them that'll come out, two x's, and just a single y. So we have x squared over, not an x squared over y. Then we have the next one. We have m, and we can break down the n's as n to the 5th, n to the 4th. So notice we need one more n, so let's multiply by 5th root of n over 5th root of n to add one more n here. So then we would have m times 5th root of n all over, and there's 2 n's to the 5th now, n squared. Last, we can break down the y to the 16th to y4, 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 so those 4 groups of y's. And then the top, there's just a single x to the 4th, 4th root of x to the 4th, so a single x. So the final answer is x, y to the 4th.